Hello everyone. Today's topic is the matrix representation of linear transformation. Now we have studied linear transformations by examining their range spaces and null spaces. In this section we will learn about the representation of a linear transformation by a matrix. First, let me introduce definition of ordered basis. Let V be a finite dimensional vector space. An ordered basis for V is a basis endowed with a specific order. That is, an ordered basis for V is a finite sequence of linearly independent vectors that generates V. For example, if suppose you have in F3 beta equal to E1, E2, E3 is an ordered basis. Then if we consider gamma equal to E2, E1, E3, then beta is not equal to gamma as ordered basis. That is, now order of E1, E2, E3 matters. Now for a vector space Fn, we call E1, E2 till En the standard ordered basis for Fn, and for space P and F, polynomials of degree at most n over f, we call this the set 1x, x square, so on till x to the power n as the standard ordered basis for P and F. Now, if suppose beta equal to u1, u2 till un is an ordered basis for finite dimensional vector space, then for any x in V, let a1, a2, an be the unique scalar such that x is equal to summation I equal to 1 to n ai ui. Now we define the coordinate vector of x relative to beta denoted by square bracket x subscript beta as all the coefficient written column wise, so that is equal to a1, a2, an in column. For example, if suppose your V is equal to P2R, then beta, the standard basis, is equal to 1x, x square. Now fx is equal to 4 plus 6x minus 7x square. So this is 4 into 1 plus 6 into x minus 7 into x square. So coefficients are 4, 6 and minus 7 that are written column wise. So f beta is equal to 4, 6 and minus 7. Now suppose that V and W are two finite dimensional vector spaces with ordered basis beta equal to V1, V2, Vn and gamma equal to W1, W2, Wn respectively. Let T from V to W be a linear now. Then for each j, for j lying between 1 to n, we have scalars aij such that each t of vj is equal to summation I equal to 1 to n aij wi. So basically we are taking image of every basis element. Vi's are the basis element, so we are calculating t of vj. Now t of vj will be in w, basis for w is gamma, so we can express t vj in terms of gamma, so that is equal to summation aij wi. Now the M cross n matrix defined by aij, which is the matrix representation of the linear transformation in the ordered basis of beta gamma, will be all the coefficients written column wise. For example, let us see this. If you have a linear map T from R2 to R3 defined by this mapping, T of A1, A2 is A1 plus 3A2, 0, 2A1 minus 4A2. Beta and gamma are the standard bases of R2 and R3. So beta is equal to E1, E2 and gamma is equal to E1, E2, E3. E1 is 1, 0, 1 is at the first position. So T of 1, 0 is according to the map given 1, 0, 2. So that is equal to 1 into E1 plus 0 into E2 plus 2 into E3. And similarly we calculate T of 0, 1, that will be 3, 0 minus 4. So that is equal to 3 E1 plus 0 E2 minus 4 E3. Hence the mapping T beta gamma, the first beta corresponding to R2 is written below, above is the gamma, that is equal to 1, 0, 2 and second column is T of 0, 1, 3, 0 minus 4. Now if suppose we change the basis gamma dash to E3, E2, E1, then again proceeding similarly we get this matrix 2, 0, 1 minus 4, 0, 3. Next example, if you have a mapping from P3R to P2R defined by T of fx is f dash x. So standard basis for P3R is 1x, x square, x cube and basis for P2R is 1x, x square. So define T of 1, T of x square, T of x cube. Write that in terms of 1x and x square. or write all the coefficients column wise. So T of 1, first column will be 0 0 0, second column will be 1 0 0, next column 0 2 0 and last 0 0 3. So in this way we will get the matrix corresponding to the linear transformation. Now if suppose T and U are arbitrary function from V to W, where V and W are vector spaces over F, then we can define T plus U mapping from V to W as T plus U of X is Tx plus Ux, and AT from V to W as AT of X is A times T of X for every X in V. Now we can see that this mapping is linear. So see this theorem that for all A belonging to F, AT plus U is a linear map. So to show it is linear, we have to show that AT plus U of Cx plus Y is equal to C times AT plus U applied to X plus AT plus U applied to Y. So consider AT plus U applied to Cx plus Y. So this is equal to AT applied to Cx plus Y plus U applied to Cx plus Y. This is by definition of addition of mapping. Now the first function is equal to 8 of T of Cx plus Y plus C of Ux plus Uy, because U is a linear map. Similarly we have T is a linear map, so apply that. Finally we are getting AC Tx plus Cuy plus ATY plus Uy. Rearrange this, we will get C times AT plus U applied to X plus AT plus U applied to Y. So we get that AT plus U is a linear map. Now using the operations of addition and scalar multiplication, we can get that collection of all linear transformations from V to W is a vector space over F. Now clearly this vector space is non-empty because the zero transformation T naught belong to this vector space. Now we can easily show all properties of vector spaces and we can show that this will form a vector space over F. Next we have V and W are two vector spaces over F, and we denote the vector spaces of all linear transformations from V to W by L of V to W. If suppose V is equal to W, we write LV. So next theorem, let V and W be finite dimensional vector spaces with ordered basis beta and gamma respectively, and let TU from V to W be linear transformations. Then the matrix corresponding to T plus U will be same as matrix corresponding to T plus matrix corresponding to U, and similarly matrix corresponding to AT will be same as A into matrix corresponding to linear transformation T with respect to beta and gamma. So let us take two bases, beta and gamma. So beta is equal to V1 to Vn and gamma is equal to W1 to Wn. So now there exist scalars Aij and Bij such that T of Vj is summation I equal to 1 to m Aij Wi, and U of Vj is equal to summation I equal to 1 to m Bij Wi. T plus U of Vj is summation I equal to 1 to m Aij plus Bij Wi. So corresponding matrix will be Aij plus Bij, which is equal to Aij is matrix corresponding to T and Bij is matrix corresponding to U. So we get this A part. Similarly we can do the second part also. Let us see this example illustrating this theorem. If you have these two mappings T and U from R2 to R3 given by this, T of A1, A2 is A1 plus 3A2, 0 to A1 minus 4A2, and U mapping is A1 minus A2, comma 2A1, comma 3A1 plus 2A2. So beta and gamma are the standard bases. Construct two matrices of T and U. You will get these two matrices. Now compute T plus U. You will see that matrix corresponding to linear transformation T plus U is same as matrix sum of matrix corresponding to linear transformation T and linear transformation U. Thank you for watching this video.